right? Two different and separate inputs that have the same hash. If you're only storing the hash, which you should be, of a password, you can log into that account with either of those inputs because you're only comparing the hash you generate with the hash that is stored. So both of those generate the same hash, so you will always be able to log in with either password, right? So this is bad, but it's worse if an attacker can then find a collision for a given message. So if they know what the hash is, hash functions become insecure when you can generate a collision that has the same output hash, right? So let's say I don't know what your password is, but I think this has happened in MD5 hashing, but because I have your hash value, I can generate a password that has the same output hash value, allowing me to log in as you. I'm not going to go into the maths of this because I don't fully understand the maths of it. It's incredibly complicated. It's incredibly cool. And I actually wish I did understand the maths of it. But if you can force a collision given an output hash, that's when hashing functions become insecure. So MD5 attacks have been found for MD5 where attackers can create a pair of colliding messages, right? Various demos have been created, and you can go search these online with colliding SSL certificates and colliding executables. I do have an example somewhere in my files, but it's way easier to just Google this online and see the demos there. They will explain it better than I can, right? Then there's also the secure hashing algorithm, which has three kind of hashing algorithms to it. It is a family of hashes. There is SHA-1, SHA-2, and SHA-3, right? SHA-1 is considered insecure because public collisions were found in 2017. SHA-2 doesn't have known issues. It's very widely used. You'll see it quite often. And then just SHA-3 is the new shiny, so to say. New design, it's very different. It's just not widely used yet. But SHA-2 and SHA-3 are generally okay. One of the important things here is the size of the key used for hashing. So the bigger the number on the right, the more secure the hashing algorithm is. SHA-1 in general, not good, don't use it. So how do we crack a password hash, right? That's a very good question because if I get a list of hashes, right? Now I'm going to take us a little bit to the side on story time. In network security, there's something really cool called a DC sync attack, a domain controller synchronization attack. Basically, in networks, all passwords are stored in something called a domain controller. And this attack just says, I'm a domain controller, send me all the passwords. And it sends you a list of every user's password in a network. And you get all of those, they're stored in NT hashes. It's very cool to see. It's one of the fantastic things of being a network security consultant when you get to that point, because I believe you can. Whereas you just see a whole bunch of password hashes coming in, right? First thing you need to do is you need to identify what is the format of that hash, right? Because this is a known thing, I can tell you it's NT hashing, but on Linux, you can use something as hash ID. You just echo the hash, you pipe it through to hash ID. I don't know what the Windows equivalent of it is. I'm sure there is one. And then from there, because we cannot get the input of a hash function from the output, what we do is we have a list of passwords and we generate a hash from the passwords. And then we compare the generated hash of the hashes we have in the list. And that way, if the hash matches, we know we found the input, right? What we're doing with cracking hashes is we're not taking the output and reversing it. We're taking a huge list of inputs and seeing which hashes those generate match the hashes we have. And if they match, then we know we have a valid password, right? And then if it matches, you know you have found the original password, or technically you may have found a collision. This is a very cool thing. When you do CTF challenges as well, you can sometimes you can do a DC sync attack. One of the coolest things I've done personally as a consultant is you get this DC sync, you crack the DC sync and you just hear passwords come out and you're like, wow, I've cracked this. It's really cool to see. The Try Hack Me Red Team Capstone Challenge is a good example where if you can get to the end, you can perform this kind of attack. Cool, practical demo time. But first, I'm going to jump into some Q&A. So just jumping over here. Okay, I am not sharing content anymore. 1 second. Let me just refresh this. I can see a lot of the, can a hash function be compromised? So hash functions are actually public. It's one of the security features, or security features wrong with it. It's better to have a hash function be public so that people out there can go and find hash collisions with you or for you, so that you know where the problems are, so you can update the function to remove those collisions, right? This is the kind of thing where many eyes on it, finding the problems or not finding the problems, is better than few eyes avoiding the problems, right? So hash functions, all the common ones are public knowledge, and then there's a whole bunch of cryptographic bug bounties that people go and try and crack the hash functions. And that will be GoBuster. What is the industry standard for public and private key for encryption? RSA was very popular and it's still in use nowadays. Currently, more and more, I'm seeing elliptical curve. I would go and do some research into the maths behind that. Just there's two important things. One is you use a secure algorithm for generating the encryption. The second one is the size of the key you use for the encryption is large enough, right? So I believe anything that's below 1024 bytes is considered insecure because it becomes too easy to break the encryption and decrypt that. Rather use something larger like 2096 or above bytes.